Hi, welcome to this introductory video on the PGA module. I'm Hadi Murati, an application engineer at Texas Instruments. In this video, I'm going to talk about C2000 PGA module and its use cases. First, I'll go over the main features of Type 2 PGA. Then, I'll be providing the use cases can be implemented using Type 2 PGA. For more information on peripheral types, see the C2000 Real-Time Control MCU Peripherals Reference Guide. The link is given in the end of this video. I hope you will find this presentation informative and engaging. Let's start with a question. What is the PGA? PGA stands for Programmable Gain Amplifier. This module has an operational amplifier with an internal gain network that can be changed from 2x to 64x. PGA module has fully differential and rail-to-rail inputs, high input impedance, wide bandwidth, and low output impedance. These features allow the PGA module to easily interface a wide range of input signals and fit them to the low voltage domain of analog to digital converters. Embedded on the microcontroller, the PGA module is compatible with downstream ADC and comparator modules. This reduces the size and complexity of the signal condition system and helps designer to easily use the PGA. Reducing the BOM cost is another advantages of using on-chip PGA. These features make the PGA module a high-performance analog front-end for different applications, such as signal conditioning, fault protection, and real-time control. Accurate and precise measurement is one of the main requirements for these applications. There are 4 main stages in the PGA module for signal conditioning. Gain selection stage provides different values of gains based on the operation modes. It offers 2x to 64x gain in non-inverting mode, and -1 to 63x in inverting mode. The mode selection stage provides different operation modes, including buffer mode, non-inverting mode, subtractor mode, and standalone mode. The chopper stage reduces 1/f noise and ensures performance stability of module across a wide range of temperature and throughout its lifetime. Filter stage enables removing high-frequency noises due to the power circuit switching. In an electronic system, signal sources differ in their ability to drive the capacitive sample and hold circuit of an ADC. For example, to sense a high voltage signal, using a resistor voltage divider is inevitable. To minimize the power loss, the value of the resistor should be high enough. However, combination of the high value resistor and input capacitance of the ADC circuit makes it difficult to select a sample and hold duration that is long enough for this circuit to achieve acceptable settling performance. Selecting a long sampling time is the first solution to avoid this problem. However, it limits the sampling rate, which affects the performance of the control system. Using a buffer for driving the ADC is another solution. Buffer can isolate the ADC from high impedance circuit. Since the PGA module is compatible with ADC module, using embedded PGA frees up the designer to focus on other aspects of the system. Also, it reduces number of components as well as the cost. In portable electronic designs, measuring battery voltage and current is crucial to maximize battery life and storage capacity. A battery monitoring system can benefit by integrating the op-amps and ADC modules to perform these monitoring or measurement tasks all within a microcontroller. Embedded algorithms can leverage the internally measured information to create optimized tracking of battery status and health. Low-side current sensing is another use case, where the voltage is measured across a sense resistor that is placed between the load and ground. Low-side current measurement is critical for overcurrent protection, feedback control system, and power supply monitoring. The PGA uses only one pin to sense the voltage drop directly across the sense resistor. If a higher level of accuracy is needed, the PGA can deliver a higher level of accuracy by measuring directly voltage across the resistor using 2 pins, thus removing any voltage drops from the resistor to the PCB ground. The PGA integrates the gain setting resistors, reducing PCB area and improving the accuracy over discrete implementations that use external resistors. Since the resistors are incorporated into the integrated circuit, the matching and drift characteristics of the resistors are extremely good. This offers reduced gain error and improved common mode rejection over low-cost discrete implementations. Precise current measurement plays an important role in motor drive applications as it can reduce the torque ripple, increase the accuracy of speed and torque, and improve the efficiency. This slide shows the 3-phase current measurement of a motor using 3 PGA modules. In applications that requires multiple PGAs with a common negative sense point, the PGA module offers the sharing of a common negative sense point across modules. This feature helps save 2 pins for other functionalities, such as ADC pin and digital inputs and outputs. This feature, combined with rail-to-rail input and output, high bandwidth, and high slew rate, makes the PGA module more appealing for motor drive applications. Bidirectional current sensing can be used for different applications. For example, a battery monitoring system uses a bidirectional current sense amplifier for measuring the charging and discharging currents of a battery. The magnitude of the output voltage is proportional to the magnitude of the charging or discharging current. This allows the battery monitoring system to accurately measure the current flowing into and out of the battery. As shown in here, the PGA module, in combination with dock and ADC modules, senses the current flow through a sense resistor in both directions. The C2000 device benefits from the integration of measurement circuitry, and provides a simplified design with less number of components. Quick detection of overshoots and undershoots is critical to the operation of real-time control systems. However, in reality, any transient phenomenon often has coupled noise, which can cause false trips and shutdowns, resulting in reliability issues in system functionality. The PGA module on the C2000 device not only buffers the sensor output and drive the ADC inputs, but also has configurable filter resistors integrated into the device to reduce the input bandwidth, which minimizes the out-of-band noise. Two types of low-pass filters can be implemented using internal resistors of the PGA module. As shown in figure, the combination of an on-chip resistor and an external capacitor creates a low-pass filter that can limit the bandwidth of the ADC input signal. The user can choose the value of the capacitor to meet the cutoff frequency requirement to suit their specific needs. Some applications cannot tolerate having an RC network at the output of the amplifier. Amplifier output current flowing through the filter resistor creates a voltage offset that introduces output error. In this case, one can filter the noise spikes by placing a feedback capacitor across the feedback loop. This capacitor can compensate for the zero created by the feedback network and the input capacitance of the PGA module. That concludes the PGA Type-2 use cases. To end off this video, I've noted some helpful resources that TI provides to help you expand your knowledge on the PGA peripheral. You can find more information about the PGA using the resources on the screen. You can visit our training modules located at C2000 Academy or deep dive into specific PGA use cases with the app note.